everyone, today I'm going to explain another example question. Okay, so now let's start reading this question. So this question is saying a sealed flask, right? And you have this 0.5 moles of iodine, 0.5 moles of bromine. Okay, and then another important sentence we probably should notice is it says when this container achieve equilibrium. Okay, and then this is what you have. Okay, so which means the ones that I highlighted yellow, right? Those are what? Those is initial, right? Initially what you have, right? Okay, so initially that's the two reactants you had, and then at equilibrium, then you have this. Okay, so you have that much of the 0.84 moles of IBR. Okay, so that's the information we're given. Okay, so and then it's asking you about KEQ. Okay, so now let's start writing out. Okay, so if we want KEQ, how are we gonna calculate this, right? So we all should know how to express KEQ, right? So we need a product. Okay, and then over reactants, don't forget to raise to the power of their coefficients. And then for this equation, right? So you have that. Don't forget about this too, right? That's from the coefficients. Okay. So those are the three things we need. Okay. And then you go, what do I already know? Okay. So you say again the sentence I highlighted in pink. It says when reach equilibrium, and you have the concentration. So we have this. This is actually 0.84. But that's moles. Is this concentration? No, I have to calculate, right? So now is the time we use that liter. You're gonna turn that into molarity. Okay, so that's something don't forget to do. And then these two we don't know. Okay, we need to calculate. Okay, how are we gonna calculate those two? Again, since initial and equilibrium are involved, we have to do ICE table. Okay, so that's something we're clear about. And let's start to set up our ICE table. Okay, so the ICE table again is all gas and 2 IBR. So it's gas. Okay, so I'm gonna set up our ICE table real quick. Okay, so now let's finish this ICE table. Okay, so then you have ICE. Remember the ICE table we're gonna calculate based on molarity, okay? And then we're gonna calculate that real quick. And then for this particular question, it's not bad because it's just 1 liter, okay? So in terms of concentration, right? So that will be 0.5 mole divided by 1 liter. Okay, so mathematically you get the same value, 0.5 molar. Okay, and now of course over here is 0.5 molar. Okay, and then this will be 0.84 molar. Okay, so those are the values we already know. So let's actually put them in. Okay, so we have this 0.5, 0.5, and this is what? 0. Remember, if it's now implied, that's 0. Okay, and then you have this 0.84, which is at equilibrium. All these values are we know. Okay, and then you go, what do we do? Okay, how do we figure out the change? And of course, we see, you know initial, you know final. Of course, we know the change, right? So the change will be the difference is 0.84 molar. Okay, so 0.84 molar, that's a change for IBR. But remember, change follows what? Follows the ratio from the coefficients. Okay, so that'll be 1 to 1 to 2 ratio. Okay, so remember, when we didn't know the change, this is what we do, right? So this is 2x. Okay, and then the other thing you sort of could already predict for this particular reaction is you have reactants and you have 0 products, which gonna give you Q is what? It's 0. Okay, so that direction will go to the forward direction, so the product will be positive, the reactants will be negative, right? Okay, so those are the things we have been talking about. And then if you know 2x equals to 0.84 molar, okay, well, the x will be 0.42, okay? So then now, since the products will goes by the coefficients 2x ratios, and this will be negative x and negative x, okay? As we just talk about x equals to what? X just I'll just use the value, okay, so that'll be 0.42. Okay, over here also will be 0.42 molar. Okay, so that's what we just calculated. Okay, and now can we figure out the concentrations at equilibrium? Yes, we could, right? Just math. Initial. Now initial is 0.5 minus 0.42. That will be 0.08. Okay, I'll give it the suffix wise. Okay, so that's what we have. Okay, so those are the value we have. If you want to keep all the suffix, you can add zeros to all these values. Okay, and then again for the exam itself, if I'm asking to put in the number, I will specify every time I specify requires three suffix like this value, right? That's perfect. Three suffix 110, and then I'll give you acceptable error bar. So just say you round it off a little bit as long as everything else is correct. Don't worry because I do accept the error bar for your final answer. Okay, no units, no scientific notation, numbers only. Okay, so that's what we have. Anyway, so back to this question. Okay, so now you have all the concentrations at equilibrium. So now we can use our expression to finish the calculation, right? So Keq will equals to, okay, so the product 0.84 will be squared. Don't forget because the coefficient, right? Okay, and then over 0.08. 0.08. Okay, so we do this calculation, the number turns out to be 110. Okay, so 110, the choice will be C. Okay, so this is how you do this type of question. Again, still as table, and then but instead of given with equilibrium constant, you're solving one of the equilibrium concentrations. Now you're given with the initials with one of the equilibrium and your equilibrium concentration, you're actually calculating the equilibrium constant. Okay, so this is simple question, and hopefully this is helpful, and thank you for watching.